Hello everyone, welcome back to the series on programming robot mechanics. In this video, we are going to work on trajectory planning. Well, for the couple of videos from now, we are going to work on trajectory planning, various aspects and algorithms related to it. As I said in the previous video, we were going to work with robot dynamics, but we are not actually going to take it up yet. There are actually two reasons to that. Robot dynamics is a lot of mathematics things, so the videos would get kind of boring to say, because I would be implementing the math and all. Other than that, robot dynamics is in itself a tough thing to implement because there's a lot of math involved. We would be approaching it when we are going to talk about the control of the robot. And this is also one of the other reason, because the dynamics of the robots, they are mainly used in the control of the robots. So we are not going to touch it until we reach the control part. Till then, till we reach it, we are going to work on trajectory planning. Trajectory planning has a lot of stuff again that we can do, but we're going to limit ourselves just a little bit and get on with it. So let's do this then. All right, now trajectory planning actually comprises of two subparts. Now what trajectory planning is actually, path planning and trajectory planning are slightly different if we define them differently. Path planning is selecting a path for a robot that the robot can follow. That's all right, there can be a path. But trajectory planning actually assigns a time-based schedule to that path. For instance, at every point of time in that path that the robot is going to follow, what the robot's position should be at each time instant, should be its velocity, and what should be its acceleration. All these all this time schedule actually governs the area of trajectory planning. So we are not working with path planning right now. We are only working with trajectory planning right now, right? And trajectory planning can be done in two ways. Now these are obvious two ways that one can think of. Either we can do it in the joint space, or we can say like we can set the joint positions one by one, or we can do it in the Cartesian space, which is it, we can measure the points that are on the path and convert them back to joints and then interpolate the path. So both of these methods have their own pros and cons. Trajectory planning in Cartesian space, the trajectory planning is slightly slower because we have to do inverse kinematics every now and then. But yeah, and it is better for finding collisions in the path. For a joint space trajectory, it is relatively faster, but it is a slight challenge, but not that it is not possible. It is a slight challenging thing to avoid obstacles. So that's the difference between the two. Right now, we are going to work on joint space trajectory. Maybe in the future, we can work on Cartesian trajectories as well, but let's just keep our focus on joint space trajectories for now. And the thing that we're going to implement in this video is going to be point-to-point cubic trajectory planning. Now, what does this mean by point-to-point? If we are given the initial position and the final position, and the robot has to go from the initial to final using a cubic polynomial interpolation. Other than point-to-point, we can have a point via points. We can have a set of points a robot has to follow, and the robot then forms a trajectory through it. That is one way, and point-to-point is the simplest version of all, and using cubic, it gets even simpler. And then in the next video, maybe we can take a quintic and then linear with blend. But in this video, we're going to focus on point-to-point cubic. All right, now let's talk some more theory about it. Now, cubic interpolation simply means that we have to find a polynomial. Finding a polynomial simply means finding its coefficients A0, A1, A2, A3 that are with respect to time. And we are given the constraints that we have the joint velocity and, right, yeah, we have the joint velocity at the start and the joint velocity at the end. Usually these are going to be 0, but we will provide the flexibility to adjust these values as well. Right, and then we solve this polynomial. Now this polynomial solution is actually derived in the book that we have. A0 is going to be theta naught, that is the initial position. A1 is going to be 0, A2 is going to be this expression, and A3 is going to be this expression. And we're just simply going to code this on our computer. Right. Now, one would ask why cubic polynomials work. Cubic polynomials have actually 4 parameters that we want to solve: A0, A1, A2, A3. And there are 4 conditions that we are given: the initial position, the final position, the initial velocity, and the final velocity. That's why we're using cubic. For quintic polynomials, well, we will discuss quintic in the other video. So let's get on with the cubic now. All right, now let's do this. Okay, so first let's import numpy and define a function. Oh, and we are going to put the code for trajectory planning in some other file that called trajectory.py. Now this is because considering some software development perspectives, since we're going to have different algorithms for trajectories, it is better to have them in a separate file, and then we can, in the robot class, we can on our demand call whichever method that we want to use. So we are defining the algorithms in one, and then we are going to use them in the other file. That's a simple software engineering practice just to keep things modular and working. So let's do this. I think we are going to simply have a function. Let's define that. And we are going to take Q0, that is the initial, QF final position, QD0, the initial velocity, and QF0, no, right? No, QD0, QDF, yeah. And we are going to set these as default to 0, because usually these are 0, but if a user wants, they can adjust it as they want. And let's add some documentation for this. Yeah, one thing that we're adding is an M parameter over here. So one thing that I am thinking of is the Q0 and QF, these are supposed to be joint position and joint velocity. Yeah, all these Qs, they are going to be joint values. So these are not going to be simply 0, but instead an array, or to say. So let's just not keep them, we would not be able to keep them as 0 initializations. This is because we don't know the degree of freedom of the robot, so we won't be able to adjust for it. Now, right, and okay, so these Q0, QF, QD0, and QDF is actually going to be an array of the length of degree of freedom of the robot, and that's what we're going to interpolate on, right? And the thing about inverse kinematics, now how this trajectory planning is going to fit in the overall picture is something like this. A user can give the robot the initial position in the XYZ and or roll pitch yaw as well, and the final position as well. Then we are going to compute the inverse kinematics of both of these positions. This is going to give us the joint values we have in the starting and the joint values we have in the end. Then these joint values are going to be passed to these functions, these trajectory planning functions. And then it's going to give us a time sequence of the position, velocity, and acceleration. So that's how the overall flow of this complete thing is going to look like. All right, now let's start with this. Okay, first let's add the size of the array, just to know. And what is this? M is the discrete time steps. This is, we are assuming that the robot planning that we're going to do is going to last for 1 second. So this discrete time steps is to just divide how much the 1 second is going to be split. That's how we have it. Okay. All right. So the first thing that we should do is solve for the cubic polynomial, and we are going to solve for its coefficient first. So let's see. Now these are the values. We're just going to take them and put them over there. All right, let's just get now why we are doing this np.copy is because these values are going to be passed by reference all in all. So what this means, if we just keep a0 equals q0, what this implies is if we make a change in A0, the same change is going to be implemented in Q0 as well. And that is not what we require. These two are actually separate values. That's why we're doing np.copy to make a separate list of values for A0. Right, let's now implement A2. Fine. All right. So since we are taking the time frame to be 0 to 1 second, so TF over here is going to be 1. So it's actually A2 is going to be 3 times theta F minus theta 0. Okay, we have these polynomial parameters. And as you may notice, this is actually a matrix of parameters. So we're going to use that. We're going to use a matrix actually. Okay. All right. So I realized that we were doing a mistake over here, which was we were actually copying the equation in which we were assuming that the initial velocity and the final joint velocities are equal to 0. But this is not the case that we have. We are going to make a general function for that. That's why now we're going to take this equation this set of equations that we have over here. So let's do this then. Now let's re-roll everything that we have done. And we are going to use this numpy function called linspace. What this is going to do is going to divide the 0 to 1 segment into m segments. So we have the 0 to 1 and we're going to divide this into m segments. Now what we have, we are not going to work with continuous variables as we have in this case. Right, in this theta of t, we are in theoretical perspectives, we can have t as a continuous variable, but for computers, we cannot have this discrete variable t. We are going to have this discrete variable t. We cannot have continuous variables. So that's why we are assuming that we have a segment from 0 to 1 of time that we're going to divide into m subsegments. And then we are going to put the values of those m subsegments that we got into this equation to get the overall interpolation that we have. Right. Okay. And what, all right. We have this q as q. We are going to initialize these three variables or lists that we're going to output in finally that we have over here return. We are going to initialize them with zeros because we are going to be returning a list that is going to be of this size. And then we'll loop over the time steps that we have t, and we are going to t square and t cube. We are going to make these variables available for the calculations. Then we're going to compute qi, qdi, and qddi. Qi is simply the cubic polynomial function. QDI is the derivative of this QI, and Q double D is going to be the derivative of QD in turn. And then we're going to returning it. All right, now the next step we are going to do is we are not going to yet make unit tests for now. For unit test, what we can do, we will add the unit tests for cubic, quintic, and this linear with blend function together. For now, we are going to program this visualize function. So to see how the trajectory of all these joints looks. So let's do that. Okay. Let's name that plot joint trajectory. Okay. And okay, so we can simply have this QR. Position, we are going to pass in position and the, what do you say this? Velocity and the acceleration. And we're going to plot all of these over here. So let's have some documentation first. We are again going to have that time steps thing that we had. Overall, in the complete library that we are assuming that we are working with 0 to 1 scale. So that's what we're going to do. We're going to add this linspace over here. And initial is going to be 0, 1, and the number of time steps is going to be num. Right, num. Okay. This is going to be, let's define this n over here. All right, this is the size of this is not going to be degree of freedom cross x. This is actually going to equal degree of freedom cross m, we can say. M is the time steps that we are dividing the whole trajectory for. Like this. And then we're going to set num is equal to m. Okay. And we are now going to have a variable named n. This is going to define the degree of freedom, and we're going to loop over this and plot each joint trajectory one by one. So let's do that. And x value is going to be the time. So it's going to be time steps I. And the value that we are going to plot is q0, I think, right? No, qi. Right, now this is going to plot the position. And right, and we're going to have similar 3 functions more to okay, so this is what I'm thinking. We are going to have 3 subplots placed vertically. In the first one, we're going to have joint position. In the second one, we're going to joint velocity. And the third one, we are going to have joint acceleration. So this is going to form the first subplot. So let's just see how we can implement subplots in matplotlib. Now we're going to call this function plt.subplots, which you are going to have 3 subplots. We know that. And the super title, we are going to have a subtitle. Yeah, we are going to have that as joint trajectories. And we are going to plot this in this axis. Okay, now we're going to have 3 loops similar to this. Let's do that. Now we also need to set the title for each of these. Okay, and we're going to do this just above the loop that we're starting for. And we also need to set the X label and Y label as well, which we are going to do something like this. The X label is going to be the time and Y label is going to be the respective parameter that we're measuring. Right. Now, one thing that we also need to do is add a legend. Otherwise, we won't be able to recognize what the color of each of these is. Now, one way that I am thinking of doing is like this. Like we can take the axis.0 and we can add the legend like this to whatever value that we want. We're going to take it joint. We're going to format this string and we're going to add joint I plus 1. And we're going to do this similar for all the other subplots as well. This is going to allow us to differentiate what each plot of each joint is looking like. Okay, we'll also add some comments to just clean the code up over here. Now we are finally going to test how this visualize function looks like in the main.py file. Now we have this bunch of things that we had done previously. And we're going to import from robot.trajectory trajectory planning, and from tools.visualize import plot joint trajectory. Okay. All right. Now we are going to set the initial values as something. Let's take this to be a 3 degree of freedom robot, as we usually do. And we're going to start with 0, 0, 0. And the initial velocity is also going to be 0, 0, 0. Since we're not unit testing over here, we're just seeing how the plot is looking like. That's why we're not just going to focus much on the values very much. This, we can set this to be 1, 1, 1. And we can set QDF is equal to the same 0. Since we are starting from 0 velocity and we are ending at 0 velocity. And one thing that we can do, we can keep m as a optional variable. Since users won't actually want to adjust the value of m, we will just keep it m as 100. So we are going to divide 0 to 1 segment into 100 segments, and we're going to keep this optional. So that's why we have some user experience. Okay, and okay, right. So we are going to get Q, QD, and QDD, which is going to be getting from this Q0, QF, QD0, and QD. Right, and now we're going to plot these joint trajectory. Q, QD, QD. All right, let's test this then. Oh, right. All right, I can see. So this Q, QD, and QDD are not going to be equal to single 1 cross m. These are actually going to equal degree of freedom cross m. That's the complete shape of these metrics. So since we are taking that Q0 dot shape 0, so degree of freedom is equal to n. We are going to use this m, n to get the complete shape. And the assignment that we're doing over here, QI, is actually going to set all the rows one by one, rows or columns. Let me think. There is some mistake over here. Let's deal with that. So we have n rows, we can say n rows and m columns. Okay, we are adding the value of all the, right. So in the rows, we have like joint 1, joint 2, joint 3, joint 4. And over these column values, we have time step 1, time step 2, time step 3, time step 4, and so on. Now, what we are in this loop, what we are doing, we are adding the values of columns over here, one by one. And we are doing this through, we are selecting, row into column. So we are selecting the column over here and we are selecting all the rows, right? Okay. Okay, so this is fine. This assignment thing we are doing is fine. And now let's check the shape. What is it? The shape is actually Q0's shape, which is N. So we are doing the right thing. We are adding the columns equal to the number of degrees over here. Right, now let's check and run. Okay, I get it. What we need to do is to the np.zeros, we need to pass in a tuple. That was the thing that we were missing. The shape is actually a tuple in this. All right, now this is an error that's coming from visualize.py and it says, let's deal how we are working with it. Okay, so Q is being passed as a joint position, like it's a matrix. All right. So N is the degree of freedom. Okay, so we need the, okay, all right. So we didn't need to pass that. And we have this degree of freedom over there. And we're looping over all those. So in this case, we are selecting a particular row. Something like this. We are selecting the ith row because ith row represents the ith joint. So we are plotting the ith joint we have. Now this thing is similar to this thing. we can either put the comma colon, or we can choose to ignore it, because these two signify the same thing. The only problem was that we are selecting the time steps I. Time steps is going to be passed in as is because it's a 100 sized array. Okay, it works, but we don't see the plot that we had. So let's do plt.show. Okay, as we can see, okay, right. Since all of them are overlapping, that's why it's appearing like this. Let's just fix this thing that the velocity title is covering up the position graph. And let's change these values of JOI. Oh, okay. The legend thing, okay. All right, so we need to pass a list actually to the legend in order to make that work. That's why it's JOI. Okay. And we also need to change the index of the axis. That's done. And now we need to see how to make that graph subplots that we have a little bit space oriented. The way to deal with that is to use this tight layout function. All right. And in the main.py file, we are going to adjust this to 0, 1, 2 and 1, 2, 3. All right, so here we have this. Let's enlarge it. Oh. So all these graphs are similar, exactly similar, because we have this joint position, and we see we don't have this legend over here. Let's see why we got that wrong. Anyways, right, I think I know why that got it wrong. First, let's analyze how the graphs are looking. So the velocity is starting from 0, increasing up till 1.5, and then again decreasing to 0. Acceleration is simply deaccelerating. It was started from 5 acceleration, got till 0 and -5. This we can see with the velocity that it started increasing and then decreased. This is because the acceleration was first positive and then it went to negative values. The overall position we can see is almost similar for these three joints. All right, and we still have some things that we need to work on, like the y-axis over here is slightly wrong, and the legend is also not too good. So let's work on these and then let's see. The changes that we did is we are going to remove these legend from the plots that we had. The mistake that we were doing was axis 0 dot set. We were actually setting this axis 0 for all these three. We're going to have the change the index of each subplot. And then now we are adding the legend towards the end. We are generating a legends array using this for loop. Now this is a inline for loop. This is actually equivalent to writing it something like this for I in range n, and then having a list to append to, like legends dot append f joint I plus 1. So this complete thing is actually equivalent to this. It's just written all in one line. And then we are just setting the legends for each of these axes. All right, now let's check if we are doing it right. All right, it now looks good. Okay, we have these three legends over here. Okay, and we have position, velocity, acceleration. Right. Okay, so this looks good. Right. Now we're not going to work on unit tests in this video. That is going to come up in after some videos. In the next video, we're going to work on this point-to-point quintic. This is not going to be much difficult. This is going to be very similar to cubic that we just did over here. And the plots are also going to be looking somewhat similar. So let's see what to get in the next video then. See you in the next video. Bye.